Hi Year 11s, this is Mr. Lim here, and this is our first of our series on AQS solutions. Okay, we're going to be dealing with a whole bunch of different stuff, so let's get started. Okay, so today we're going to be looking at solute, solvent, and solution. We're going to have a look at the definitions, the dissolving process, saturated and unsaturated, changes of solubility, and vapor pressure. Alright, so definitions, you can read all of that. Okay, these are just the things that you need to know. In general, we've done this all mostly before in year 8 or 9 or something like that. Okay, so let's have a think. For something to dissolve, what must occur? So let's have a start. Let's start at the end point. So let's say you've got some salt in some water. Let's have a think what's actually going on. You've got water particles. Okay, water particles all through here. Okay, and you've got particles of salt, which is made up of sodium, Na, plus ions, and you've got Cl minus ions as well. Okay, so that means that the Na and the Cl are, okay, that's the finished part. Okay, let's have a think about how they were at the beginning. Okay, so at the beginning you had a beaker full of water, which didn't look much different to what's there now. Okay, but we will discuss some differences in a moment. Right, and you had, sodium chloride. Why are you drawing it in a diagonal line, Mr. Lim? Well, if you remember, ionic substances are in lattices of interchanging positive and negative ions, which is why you draw it like that. Right, so what's got to happen between the reactant side and the product side? Well, what you've got to do is got to make sure that these NAs and CLs must be split apart. That makes sense, right? You've got to split them apart, otherwise they're not going to be individual particles here in the solution, right? And in here, you've also got to have the water particles split apart. Now, what does that mean? Think of a ball pit where all the kids love to play in. Okay, so if it's full of those plastic balls that kids love to play in, right? If a kid wants to get into it, right, they've got to part the balls, and then they can fit in between the balls. All right, so these plastic balls have to move apart to accommodate the substance that is between them all of a sudden. So you've got to split the H2O particles apart. All right, so you've got to split apart the solute, you've got to split apart the solvent. And one more thing that you'll learn is that we're going to actually form new bonds with the solute and solvent. So let's have a think. The bonds between the solute particles must be, and between the solvent particles must be broken. Okay, so that's what we were talking about just then. You've got to break apart the ionic substances, you've got to break apart the waters just so that they can get in between each other. And that requires energy, right? What's great is that that energy comes from solute-solvent bonds. Okay, so it's bonds between the solute and the solvent. In the case that we just had, it's between the sodium chloride and the water. That releases energy. So in general, if the bond strength between solute, which is red, and solvent, and the bond strength between solvent-solute, they must be roughly equivalent for the dissolving process to occur. Because if you don't have enough energy to break the bonds, you're not going to actually break them apart, and therefore the solvent particles and the solute particles are going to stay together. Okay, just imagine, remember it's ionic bonding. If you don't have enough energy to break those particles apart, to split them apart, you're not going to end up with individual particles. You're just going to end up with one block of sodium chloride. Okay, and therefore you're not going to really dissolve. So that's what happens when something doesn't dissolve. You don't break the solute particles or the solvent particles. Those bonds aren't broken between them, right? So that's what happens when things don't dissolve. So they're going to be roughly equivalent for the dissolving process to it, right? So what does that look like? So you need to be able to draw the solute solvent bonds that occur between different things. Okay, so let's just split up the screen into 3, right? So sometimes you will have water bonding, forming bonds with other things. All right, so if I say that I'm going to draw an ethanol here, ethanol, all right, and it's got a bond in between it here. What type of bond is that? That's a hydrogen bond, right? And you can have another hydrogen bond here with another water molecule if you wanted to. All right. All right. So this is polar and polar. When you have a solute is polar, solvent is polar. The solute is the ethanol. Okay. And the solvent is the water. And they have bonds between them, which is these things here, right? So you've got hydrogen bonds between them, between solute and solvent. And the hydrogen bonds are the same bonds between ethanol and ethanol, and the same bonds between water and water. So since they're similar, then you're going to have dissolving occur. But what happens if you've got a polar substance, like water, and a non-polar substance, like hexane? Why did I pick such a long molecule? Okay, so can you form hydrogen bonds between hexane and water? No, you cannot, because this is a non-polar solute. So this is a solute, and the solute is non-polar, which means it has dispersion forces between. This is solvent, and this is polar, which means it has hydrogen bonds in between. Right? So any bonds here that form between those are going to be only dispersion forces. And if they're only dispersion forces, the dispersion forces are not greater than the hydrogen bonding. They're not greater than the hydrogen bonding, which means that this won't dissolve, right? However, if you've got methane and hexane, what types of bonds are going to form between these ones, right? This is going to be dispersion forces. And what's going to be between these ones? This one's going to be dispersion forces as well. And what's going to be between the solvent particles? Also dispersion forces. So the dispersion forces of the new bonds are going to be roughly equal to the dispersion forces of the solute bonds and the dispersion forces of the solvent bonds, right? So they're going to be roughly the same, and therefore this will dissolve, right? That's the concept there. You have to look at what bonds are forming in the green, right? What bonds are forming in the green? What bonds have to be broken between the solvent, which sometimes is blue, sometimes is red, and what bonds are broken between the solute, which is sometimes red and sometimes blue. This one I really should have paid more attention to that. Right, so that's what you're comparing, okay? And they have to generally be the same strength, and if they're not, then they're not going to dissolve because you're not going to be able to break one set of those bonds. So, saturated, unsaturated, you can have a read of all of that, okay? Right, and then let's go talk about supersaturated for a moment because it's the most interesting one of them, okay? So, supersaturated, how do you make a supersaturated solution which holds more than it should, right? So what you do is you take your beaker full of solvent, you heat it up, and so now it is at a higher temperature. So say it's at 50 degrees Celsius, right? Now, at 50 degrees Celsius, the water can hold, say, 20 grams of whatever per 100 ml. And at, let's just say this is at 20 degrees Celsius, this can only hold 10 grams of whatever per 100 mils. Okay, so if you then add some stuff to it, you add 20 grams at 50 degrees, it'll all dissolve because you can fit 20 grams at 50 degrees into that volume of water. Okay, that 100 mils of water, you can fit all 20 grams, right, at 50 degrees. If you then cool it carefully, right, if you cool it carefully, what will happen is that it'll now be at 20 degrees Celsius. However, the solute stays dissolved. And now you've got 20 grams when only 10 grams should be there. Okay? But if you agitate it, stir it, poke it, or if you add some of the stuff in, all of a sudden, you add in one tiny drop of that solute in the solid form. All of a sudden, the 10 grams that shouldn't be there will start to make this bigger and bigger. And so that's that 10 grams comes out of solution. Right? And then you still got 10 grams in solution. But that's how you make a supersaturated solution. You heat, you add lots, you cool it down carefully, and then you don't poke it until you want to do some cool stuff with it. Okay? That's the idea. Right? Changes to solubility. Okay, so in general, solids become more soluble in liquids when the temperature is increased. That is a proportional relationship. Gases become less soluble in liquids when the temperature is increased. That's inversely proportional. And gases become more soluble in liquids when the pressure above the liquid is increased, which is a proportional increase. Proportional relationship. Okay? So you just got to memorize those ones there. Here's a diagram of that particular thing, and you can see that not all solids follow the rule that as you get hotter, it becomes more soluble. Which one doesn't? This Ce2SO4 doesn't, but most of the others do. All right, and some of them are linear, some of them are not. We can also use this to tell what is saturated or unsaturated. So let's just say I have 50 grams of KCl at 40 degrees. Okay, is it saturated or unsaturated? So first of all, then you find the 50 grams here, and you say the 40 degrees here. You see where that comes together, and it comes together here, and that is above the KCl line. All right, that KCl shows that, okay, at 40 degrees, you're really looking at over here, which would be go to here, which you're looking at about 37 and a bit grams per 100 grams of water. Right, so that would be then saturated. Okay, if say you were looking at something like, 20 grams of KNO3 at 20 degrees Celsius. Okay, so 20 grams at 20 degrees Celsius, that leads you to here. That's under the curve, so that is unsaturated. And that's how you work out saturation using this diagram. Okay? Make sense? Hope so. Okay, so let's have a think about when we have a glass of water, all right, or glass of whatever, fizzy drink. Why do the gases come out? Now, one of the questions a long time ago in WACE was, if you heat up water, how come bubbles appear at the bottom at 80 degrees Celsius instead of 100 degrees Celsius? Why? Because these are the dissolved gases in the water. Okay, not steam, not gaseous water, but dissolved gases within that water. Right, so let's have a think why. As you heat it up, the particles go faster, yeah? The particles move faster and faster and faster. Okay, now if you are a gaseous particle dissolved in all of those water particles, what's holding the water particles together? So the water to water particles are held together by H bonding. Okay, however, if you're a particle of O2, what's holding you together? Dispersion forces. If your dispersion forces break whatever is holding you there inside the dissolved substance at a lower temperature than everything else, then you're going to turn into a gas first, and that's why you get dissolved gases coming out of solution, right? In general. Okay, think about it when you also have a can of Coke, whatever, right? On the inside, there is liquid, but there's also a small amount of gas on the inside. Okay, so when you open it, you go ch, and out flows a whole bunch of gas. Okay, this gas is under pressure when sealed. Okay, so the gas is under pressure when sealed inside that can. When you open that can, the gas is no longer under pressure. If it's no longer under pressure, that means the solubility of the gases inside that liquid, has it increased or decreased? The solubility has decreased. Right, what happens if the solubility is decreased? That means they all start to come up and bubble and fizz, right? That's what happens, and that's what happens when you open up a fizzy drink. Okay. Finally, we go to vapor pressure, right? The vapor pressure exerted by particles of evaporated solvent in a closed container decreases when solute so dissolved in the solvent. So let's have a look at what that means. Okay, so let's have a closed container. So this is a jar or something, and it's now a closed container. You've got water in there, and some of that water evaporates. So you've got H2O in gaseous form at the surface. Right? Those will hit against the container walls and exert a pressure. Okay, so those will exert a pressure. If you have a greater rate of evaporation, so say this might be, instead of H2O, it would be something like ethanol, which has a weaker intermolecular forces, right? That means that you're going to have a greater rate of evaporation, and therefore you're going to have a greater vapor pressure. But that's not really the point, okay? Because if you have something that has a greater vapor pressure, that's all fine and dandy, but we need to talk about solubility. If you start adding solute particles to your solution, all right, all of a sudden you have some particles at the surface. What happens to the rate of evaporation if you've got some particles at the surface? The evaporation rate decreases. If you have less evaporation rate going, that means you have less H2O gas, and you have less H2O gas, you have less pressure. All right, and that's why the vapor pressure decreases when the solute is added. All right, that's the concept. Okay, so that's all for vapor pressure. Normally I would have had some questions, but I've got to add them in. I'll maybe add them in later on. All right, that's all.